Hello, my name is James Lin. I came from Shanghai Jiao University. I work in the university as the Vice Director of HPC Center. I thank the invitation from Kevin and Alex, and I'm so glad I have a chance to meet you guys online. Some of you may not familiar with my university. There are three things I would like to highlight. First, the university was established in 1896, and this is the second oldest university in China. Second, my university hosted several international HPC conferences, such as CC Grid in 2009 and IPDPS in 2012. Both are the first time in China. Third, my university are very strong in HPC, and we have the several supercomputers, including the one currently is the top in the China university. This one is donated by the Lenovo CEO, who is the alumni of my university. Last year, he took 100 million yuan, which is about 15 million US dollar from his own pocket, and brought a supercomputer for his alma mater. My talk is about benchmarking for processor performance variations. And here is the outline. First is the background of this research. The second, we analyze the performance variation of an ARM processor. The third is the case study, and the last is the conclusion. As I mentioned before, in my HPC center, we have several clusters. Here is another one we called Pi 2.0. This class was built in 2018. The CPU are in Intel there, and all the nodes are connected with the Omni path, which was sadly no longer developed by Intel. When we built the cluster in 2018, we found some performance variations when benchmarking the HPL on every single node. The best performance of the HPL on a single node is about 2,290 gigaflops, while the worst one is about 2,075. There is about 17% performance gap between the best one and the worst one. But please notice these CPUs are all in the same cluster. So what we did after we find the performance variations, we further diagnose the system and find the performance variation are related with the CPU frequency and the memory bandwidth. For the CPU frequency variations, we think they are CPU's bad quality leads to the frequency drops. For the memory bandwidth, we found the cluster vendors mixed 2 rand DDR4 memory and 1 rand DDR4 memory. Therefore, we asked the cluster vendors to replace the low-frequency CPUs and use all 2 rand DDR4 memory. After that, the performance abnormal was fixed. This is the real case we have experienced on the performance variations. There are many cases of performance variations, and we classified them into 4, roughly. The lowest one is on the chip that could possibly related with the design flaw in the microarchitecture, which can lead to unstable interloop performance. The second level is the OS level that could be caused by the program is interrupted by the operating system. We often call this OS noise. The third level is the node level. We have the performance variations among different nodes. The fourth level is the cluster level. We have the same jobs runs with the different time on the whole system. One thing I'd like to notice here is the different sources of performance variations can be overlapped, and therefore can increase the variations. For the chip-level performance variations, one notable related work is on Stampede-2. Dr. Bandwidth published a paper on SC 2020. He found on Stampede-2 that several random tests should slow down during the single-node HPL benchmark. This case is the same as our case when we built a cluster at my university in 2018. In this paper, he mentioned that Intel CPU has a design flaw in coherent agent that leads to an occasional cache line false evit. He then fixed the issue with the large page size and significantly increased the full system HPL result. For the OS noise, Torsten Hoffler has a work on 2010. He found that the performance degradation of NPI collective operation keeps worsening as the applications scale up on the Jiao supercomputer. The reason is the interrupts from the operating system jeopardize the internal synchronization. For the node-level performance variation, there is a paper in SC 2010 too that about the variations caused by the Intel Turbo Boost. The author tested the single-node performance MKL DGEM on the three supercomputers, CAP, Edison, and Stampede-1. They found MKL DGEM has a high utilization of 512-bit ALU and therefore triggers frequent throttling. The different quality and working environment of processor leads to the different throttling levels, which induce node-level performance variations. For the cluster level, Abinov published a paper on IPDPS 2020. He collected data on the Core supercomputer for 5 months and detected performance variations in 4 applications, which led to about 300% performance gap. He located performance variation source, which is the coupling of Dragonfly network structure and the job scheduling strategy. And inappropriate node schedule brings around about 200 seconds slowdown in the communication of the 512 node job. Then I will introduce our ongoing research study on the ARM processor. This is our experimental platform. We have the Intel Xeon Gold CPU as the baseline and use Kunpeng 920 as the research target. The Kunpeng 920 is a server-level ARM processor. It has 64 cores, and each core is 2.6 gigahertz. We use the top-down benchmark approach to diagnose the performance variations of the Kunpeng 920 processor. The approach includes 3 steps. The first, we use some mini apes, including the HPL, snap, T-leaf, and cover leaf to identify the performance anomalies. Second, once we identified them, we used micro benchmark for further investigation. The micro benchmarks are stream benched. In the third step, we use the processor hardware counter, aka PMU, performance monitoring unit, to build correlations for deep diagnosis. We use the basic assembly arithmetic instructions to evaluate the ALU performance. we have some interesting finds. First, the throughput of the FP64FMA and the MUL instruction is just halved. Second, the FP13 dive and squat instruction are not hardware-wired implemented, they are software implemented. Therefore, based on these facts, we predict the performance of mixed position application will vary in different implementations, and arithmetics with the different positions will meet in consistent performance. We use the Snap Mini apps to evaluate memory subsystem. We use two sizes of data set, the small one and the large one. The small one has the beta data locality, and the large one has more cache miss and refill. We then observe the performance drops when running large data set, and the best performance is when running with the 4 threads within each process. To further investigate, we use the micro-benchmark to evaluate memory bandwidth, the cache latency, and the latency of the inter-core data sharing. With the micro-benchmarks, we found the memory bandwidth drops in the string add and the string trade kernel, which implies the computer kernel with high arithmetic intensity is difficult to utilize the memory bandwidth. Second, the unstable level 3 cache coherence and the larger DRAM latency jeopardize the performance. When data access of a sweep process of a snap hits the level 3 and the DRAM memory in the large data set. We use the macro benchmark to evaluate the latency of inter-core data sharing. We found by making use of core affinity in the continuous 4-core cluster, the latency of the intra-core cluster access is much lower than in the other scenarios. Second, we found when the data sharing goes across the die, the latency is much higher than the intra-die access. Moreover, level 2 cache inter-die access is notably slower than the one in Intel Xeon processors. The third mini apps we use is TLEAF. TLEAF is a memory-bound proxy application that can build 3 different essential kernels. We run process with the 4-thread mapping to the 4 neighbor cores according to the experience in the snap test. We found in the 100 single-node test, Kunpeng 920 shows round-to-round performance variation with up to 3.3% performance drops compared to the best performance. But if you compare with the Intel Xeon processor, which is only about 1.2 performance drop. To further investigate this performance drop phenomena, we use the micro benchmark to evaluate the level 3 intercore access. We found the latency of level 3 cache access incur notable variations, as we can see from the figure. We also use the micro benchmark to test multiple memory bandwidth and record the minimum, average, and the best bandwidth in a 1-to-all core stream benchmark. We found the real multiple memory bandwidth incurs run-to-run performance variations. And at last, we analyzed the correlations between the bandwidth and the performance counters. We found that both L1D cache refill rate counter and the back-end store counter are linear negative correlated to the memory bandwidth. Therefore, we conclude the multi-core DRAM memory bandwidth is a performance variation source, and we argue the root cause of the performance variation may be related with the prefetch and the cache eviction. The last mini ape we use is the cover leaf. The cover leaf is used to evaluate the peer-to-peer memory peer-to-peer bandwidth and latency in NPI communications. We found the large data set has more performance gap be, between the two processes, while it has the less gap between one sock and two sock tests. We further investigate and compare the Intel processor with the Kunpeng 920 processor. We found Kunpeng 920 processor has higher latency and a steep increasing trend. And we also find that when the packet size increased, the Kunpeng 920 has a steep trend in the NPI bandwidth. Here is the summary of the performance variations on Kunpeng 920 we have studied so far. For the arithmetic instructions, the CPI of common arithmetic instructions varies in different positions, and FMA is halved in double position. It will have two impacts. One, the performance of mixed position application will vary in different implementations. Two, arithmetic with different position will meet inconsistent performance. For the cache and memory subsystem, we find variations of the bandwidth and the latency in different compute patterns and different remote access patterns, and also the run-to-run performance variation in the memory subsystem due to the design, imperfection, and cache eviction algorithm. It also has two impacts. The first, performance drops when performing inter-core clustering and inter-die data sharing. The second, performance anomaly in memory-bound applications. For the NPI communication, we find when the packet size increase, the Kunpeng 920 processor has a steep trend in the NPI bandwidth and latency. The third part of my talk will introduce a case study that we build a small HPC cluster with the Kunpeng 920 processors. The cluster has 100 nodes, and each node has two processors. The cluster nodes are connected with InfiniBand 100 gigabytes, and the system was up and in production service since last May. To trigger the performance variations of the cluster, we designed two special HPL light test cases, one for the single node and the other for 32 nodes. In the single node HPL light test, we find some nodes has low performance results. They are caused by the motherboard malfunctions. We therefore replace the motherboard of these nodes. In the 32 nodes test, we find some nodes with low performance results. While this time they are caused by the InfiniBand network adapters. Some models of the adapters are not compatible with the others. We then replace them. After that, the cluster runs very stable. It has only one hardware replacement in its first year. The system utilization is quite high, and the average is about 75%. We optimized some software and application for this ARM-based cluster. Here is the part of the list. We have the wasp, we have the amber lamp, and so on. The conclusion. We use a top-down approach to evaluate the HPC systems to find the performance variations. Here are the mini apes and benchmarks we have used in our study. The last slide, little advertisement. My university, SJTU, and the Recon CCS will host the IEEE Cluster 2024 in Shanghai, which is 2 years later. Professor Satoshi Mazuka, who is my PhD supervisor, and I will serve as the general co-chair of the conference. I hope we can have an in-person conference at that time and see you everyone in Shanghai. Thank you.